Hello again. Here with another example related to determining the magnitude of acceleration for a motion of a particle along a curved path. In this case, we have this package going along this curved path whose profile is given by this parabolic path y equal 1/16 x squared. And at point A, we are told that velocity is 15 feet per second, and the speed of this box or particle at that instant is increasing at a rate of 3 feet per second squared. So that's actually v dot, rate of change of velocity, which is actually the tangential component of acceleration. So that is given at that instant. This is, of course, at A for that particular instant. So the question here, or what we are trying to find, is what would be the magnitude of acceleration at A at this instant? So we know that magnitude of acceleration is always calculated based on the combination of two components, the a sub t and a sub n, or square root of a sub t squared plus a sub n squared. You have seen this in many other examples and in other videos. Okay, so we already have a sub t at that instant. We have to find a sub n. A sub n is v squared over rho. We also know the velocity of the package or the particle at point A is 15 feet per second. The only question is, what is rho? So the whole point of this problem is determining rho. So what would be rho? So rho, when you have the equation of the path, can be determined based on this equation. Rho equal 1 plus y prime squared raised to power 3/2 divided by absolute value of y double prime calculated at the given position based on the x. In this case, is x equal to 10 feet from our reference. All right, so let's go ahead and do the first derivative. Y prime is 2/16 of x, or 1/8 of x, and y double prime is equal to 1/8. If you go ahead and plug in for x equal 10, so you get 10/8, which is 1.25. And actually this guy, regardless, the y double prime, regardless of what x you have, is a constant, is 1/8, which is 0.125. Or you can just leave it as 1/8. So let's go ahead and plug in to this equation. Rho equal 1 plus y prime 1.25 squared raised to power 3/2 divided by 0.125, absolute value in this case positive. By the way, the only reason you have the absolute value is so that sometimes y double primes are negative, and or when you plug in the x, it becomes a negative. And because rho is just a number, it has to be positive. That's why you use the absolute value. The numerator, by the way, is always positive, regardless. So rho, actually, if you calculate rho, is about 32.82 feet. So now we are ready to go into this equation, put the velocity of 15 feet per second and square it. That's 225 divided by 32.82. So AN comes out to be about 6.856 feet per second squared. So we are done. Magnitude of acceleration at A is a sub t, which is given, is this 3 feet per second squared, plus the 6.856, the normal component squared. And if we do the calculation, that should be about 7.48. And let me go ahead and show you what's going on at this instant. So this is the tangential axis at that instant, and this is the normal axis at the instant shown, right? So basically our tangential component of acceleration is about 3 feet per second squared, or exactly 3 feet per second squared. And our normal acceleration is a little bit more than twice that. So if we draw it, to the scale that we have, this is the 6.856, right? So the resultant of the two, which is this guy, magnitude of acceleration would be then this guy. And that's the one that I calculated for you, the 7.48 feet per second squared. Okay, so this was really a simple problem. The whole point of this problem really was the fact that you can calculate rho based on this equation, this formula. So remember that anytime you have the path of the motion, equation of the path, you could actually calculate the radius of curvature at that instant based on the horizontal position of the particle from that given reference. So as always, thank you for watching and listening, and in the process I erased that. And if you like the video, you can subscribe, and I will have many videos coming your way, every week or so, or even sooner than that. Thanks again.